Silicate minerals make up 90% of the crust of the Earth. So if you want to learn about the rocks and minerals, this is the right place to start. The building block of a silicate mineral is the silica tetrahedron composed of silicon and oxygen. It has one silicon atom in the center, and it's bonded to 4 oxygens around. So the formula is SiO4. The bonds holding the silicon to the oxygen are covalent bonds, which are pretty strong bonds. The tetrahedron has a charge. A silicon ion has a valence of 4. That is, it's able to combine with 4 different atoms. So no wonder it's gone and combined with 4 oxygen. Each oxygen, however, has a valence of 2, -2. That means that it can combine with 2 things. So if you put this all together, you have +4 and 8 minus 2's, you have an overall charge of -4. That allows every tetrahedron to combine with other cations or with another tetrahedron. We can show a tetrahedron as this clump of 4 oxygen with the silicon hiding in the center there, or we can simply show it as this pyramid. Here we have isolated tetrahedra. Now remember that each corner of a tetrahedron contains an oxygen, and oxygen still has a negative charge associated with it. That means these tetrahedra are all negative, so they would repel each other. How do we keep a silicate from self-destructing? Well, we can glue it together with cations. In this example, we've used iron. The positive charge of the iron cation is attracted to the negative charge of the oxygen. This bond that it makes is an ionic bond. Now, the ionic bond is not as strong as those covalent bonds within the tetrahedron, but it does the job. You could instead use magnesium, does the same thing, or you could choose to use both magnesium and iron in any combination you wanted. That's the case with olivine, this olive green mineral. Olivine is composed of isolated tetrahedra connected together by cations. The formula FeMgSiO4 tells you that it contains isolated tetrahedrons, SiO4, but also that the iron and magnesium can substitute for each other. Having different ratios of cations like this could be called a solid solution. Next, we have single-chain tetrahedra. The oxygen that is part of this upper tetrahedron is also part of the lower, so it's covalently bonded in both directions, as is this and this and this, making it a single chain. So with all the oxygen attached above and below, they're doing double duty, and you don't need quite as many of them. However, if you get 2 chains next to each other, remember these oxygens still have a negative charge associated with them if they're not bonded in both directions. As a result, this would fall apart. What do we do to glue these chains together? Simple. We add cations, creating ionic bonds. However, these ionic bonds are not very strong, so if this mineral were to break, it would break along the ionic bonds instead of across those chains. This results in these single-chain minerals having a cleavage plane, that is, a flat surface along which it breaks very easily. One example of a single-chain silicate is the family of minerals called the pyroxenes. Pyroxenes tend to contain iron as a cation, making pyroxenes very dense, hard, and dark. A very common pyroxene that we'll be seeing a lot of is augite. Augite is this rather boring black rock with definite cleavage planes that is found in basalt. As you can see, its formula gets a little more complicated. Now, there's no sense in trying to memorize this formula, but notice that it does tell you quite a bit of information. First of all, aluminum sometimes replaces silicon. You have a 3-to-1 ratio of oxygen to silicon. Since those oxygens are doing double duty, you don't need as many. Double chains also occur. That is, 2 single chains joined together by a common oxygen. Of course, two double chains will repel each other. How do you get them to stick together? Of course, simply add cations. And once again, those ionic bonds will be the weaker bonds, and that's the way the mineral will tend to break. Double chain silicates include the amphiboles, a family of silicates. The most common example of an amphibole is hornblende. Hornblende is rarely found alone, but you've seen it a lot as those little black specks in granite. Then there are sheet silicates, where these double chain silicates are connected in all directions in a two-dimensional sheet. Mica is a great example of a sheet silicate. Clays are also sheet silicates. They result from the weathering of rocks. And although you can't see the sheets in a clay the way you can in mica, they are there and they're microscopic. And the important thing about clay sheets is that they absorb water between the sheets, giving them the ability to expand and contract. So the sheet silicates have 3 out of every 4 oxygen atoms connected to others, but that still leaves a negative charge between the sheets, and that's why they will attract cations as well as water. Finally, we have the framework silicates, in which the silicon tetrahedrons are connected in all 4 directions. Every oxygen is part of 2 tetrahedra at the same time. Therefore, there's no need for any cations. Everyone's happy. This makes most framework silicates very, very strong. The best example of a framework silicate is quartz. How elegant! It's simply SiO2. It has no cleavage planes because it is strongly bonded in all directions, but it does break with conchoidal fracture, that is, along smooth, curved surfaces. It makes for great arrowheads. It has that beautiful hexagonal crystal. There are many varieties of quartz, since a very small amount of impurity can give it a different color. We have crystalline quartz. Of course, all minerals are crystalline by definition, but by crystalline I simply mean that the crystals are large enough so that the quartz tends to look glassy. There's rose quartz and milky quartz and smoky quartz and amethyst and citrine, just to mention a few. In some quartz, the crystals are so small you cannot see them, and it doesn't look glassy. However, it's still SiO2 with small amounts of impurities, giving it all the various colors. So we have chert, agate, jasper, flint, and so many more. Feldspar is the most common mineral in the world. It's a framework silicate, but some of the aluminum has taken the place of the silicon. That leaves space for all sorts of other cations to become involved, since aluminum and silicon don't have the same valence. Potassium feldspar, as you might guess, has potassium and aluminum and silicon and oxygen. A very common variety of potassium feldspar is orthoclase. It could be either white or pink. It breaks in 2 cleavage planes almost at right angles. Another important feldspar is a plagioclase feldspar. Instead of potassium, we have either sodium or calcium. Once again, this is a solid solution with different amounts of sodium and calcium depending upon the specific kind of feldspar. If, for example, it's only sodium, you have an albite or a totally white feldspar, and if it's all calcium, you have anorthite, which is gray. But there are many combinations of sodium-calcium in between, giving us many other flavors. So the next time you look at a granite countertop, you can see little specks of black and say, oh look, there's hornblende. Or the pink is K feldspar, and the white, plagioclase. The gray would be smoky quartz, and we even have some biotite mica, which is going to be black. Hopefully, the next time you take a look at a textbook and you see something like this, you'll see that tetrahedron, SiO4, makes sense. We have our isolated, olivine, single chain, pyroxene, double chain, amphibole, sheet, muscovite, and framework silicates, feldspar, and quartz. And you look at that and say, yeah, that makes sense. If so, I've done my job.